right, everyone. Welcome back to our fourth session, first day of HAQAST. Today, we're going to have some talks concerning remote sensing for remote regions, and with I think a range of topics we're going to be covering, but some focus on dust. So to kick us off, we have Jeff Pierce, a HAQAST member from Colorado State University.
Thanks, Carl. All right, so title, satellites are needed to complement our sparse surface monitoring network for quantifying dust events. So as of this morning, Jennifer was ahead in shout outs because of Tracy. And if I haven't been in all the sessions, of course, if she's fallen behind, I'll try to put her back in the lead. So I'm going to be showing her work here. And she has a poster tonight, so you should go see that. And I want to shout out to our partners at the National Park Service and at Colorado State, and one of which is HAQAST, who also has a poster tonight on dust modeling. I'm not going to talk about her work, but you should see her poster. All right. Pork is the other white meat, and dust is the other natural aerosol problem. So there's a ton of focus in HAQAST on smoke, rightfully so. And I love showing this animation from GOES. And so this is 2022. There's big wildfire season in New Mexico coming through. But then if you just look up, you see this dust plume coming out of Colorado and sneaking in. And I want to give out a shout out to Chelsea, who's speaking next, New Mexico Department of Health, who has to deal with all this. So she'll tell you about her perspective on that. So dust, most of dust mass is in the coarse mode, meaning it's larger than 2.5 microns and smaller than 10 microns. This has sort of gotten it lost a little bit from the satellite remote sensing world, where the smaller fine mode particles tend to translate to AOD a little bit better. And so I'm going to talk today about the work that Jennifer has been doing to try to understand what other information we can get out of satellites to look at dust. Dust has a lot of overlapping health effects, and coarse PM has a lot of overlapping health effects as fine PM, such as cardiovascular respiratory diseases, radio effects, impacts on biology, as well as reduced visibility, which is where a lot of the accidental deaths come from dust. A lot of the work in trying to understand when dust events and where dust events happen comes from surface monitors. And so you have a dust event, and we have monitors in these sparse locations. And from this, you can do quantification on what the dust concentrations are. One of the great papers on this came out of Daniel Tong's group. So Daniel Tong was on the last HAQAST team when this paper came out. So this is a HAQAST paper. And what he did is the size of the red dots is how many dust events struck those in situ monitors, and the coloring of the states is how many deaths he could find that were attributable to dust events. And as you can see, the dust events tends to be in the southwest and south central, but there's a lot of space between the circles. So just to make that point, monitors are sparse, and so from the monitors alone, it's kind of hard to know how many dust events we're having, how bad is it everywhere, how large are they, and so on and so forth. So this is just, again, looking at monitors. This is a map of co-located PM10 and PM2.5 monitors. You need both to quantify the coarse, because if you just have PM10, you could be getting high concentrations from fine particulate matter, because that's part of PM10. So you need the two for differencing. But even if you were to plot one or the other, there's still significant gaps. But if you particularly look at like this whole part of Texas, eastern New Mexico, Arizona, there's hundreds of kilometers between these monitors, and there's dust events that happen there, as we saw in the animation before. So ultimately, we want to bring in, like HAQASTers do, bring in satellites. So we want to be able to increase our spatial coverage and temporal coverage, potentially getting some information about whether it's coarse or fine. Obviously, there's not always a direct relationship between what a satellite sees and what's happening at the surface, though. Clouds get in the way, nighttime happens, so on and so forth. But ultimately, we'd love to take some combined look between satellites and surface monitors to understand where dust events are happening and how bad they are. And so we're working towards having some complete picture of dust events. And this is to maybe follow in the footsteps to a degree of people who've worked on making PM2.5 products, such as Randall Martin's group that he talked about this morning. And so this is for fine particulate matter, not coarse. Dust can contribute to this as well. As you can see, obviously, there's fine dust over the Sahara, but most of the mass still is in the coarse mode. And so one of the things we can do for dust that you can't do for fine PM is you can exploit some of the information from the long wave. So long wave are wavelengths of energy that are emitted by the Earth, and they're at wavelengths that are too long for us to see. And so with most of the fine particulate matter information, they're looking at visible wavelengths or near visible wavelengths. So this is significantly longer wavelengths than that. And so the Earth is emitting energy peaking around 10 to 12 microns. And I'm just going to focus on two different wavelengths here because the GOES satellite measures both of these. 10 and 12 micron wavelengths will pass through fine particulate matter as if that particulate matter generally was not there. If a cloud is there, the cloud will absorb the radiation and then re-emit it at a colder temperature so the satellite can tell that a cloud is there. Dust is interesting because of its refractive index having a strong difference between 12 and 10. The 10 tends to be more strongly absorbed than the 12, and the 12 will pass through. So you can get information from the fact that if you're seeing like the 12 was emitted from the surface and not absorbed and re-emitted, but the 10 is, that's a strong sign that dust is there. And you can get this information from the GOES geostationary satellite that will allow you to detect potentially if dust is there from sunup to sundown. And there have been products exploiting this from the GOES satellite, such as this one here, from a number of groups, but it hasn't been systematically tested for the US for a long time period. It mostly stuck to case studies. So what Jennifer did is she looked at 7 years of data, trying to see when dust is detected and is it also detected at monitors. So this is just one of the case studies that Jennifer started with before looking at the whole 7 years in aggregate. And this is using one of those long wave detection algorithms. This is called the pink dust index. Don't have time to get into how it works or why it's called that. But ultimately, when you're above about 0.75 on this, so when you're in the light orange and yellows, it's indicative that dust is in the column. And you can see that the pinks, the sort of yellows here line up for places where your eyes can probably identify it being dusty from the true color image. And so using that threshold of 0.75, Jennifer found all the times over 7 years where it was over co-located PM10 and PM2.5 monitors to correlate it with what the coarse concentrations were. And when the pink dust index was above 0.75, almost all of the time the coarse particulate matter was over about 180 micrograms per meter cubed, so quite high coarse concentrations, peaking in this sort of 500 to 700 range. We can compare that to the many, many cases where the pink dust index is less than 0.75, in which case it's almost always in the less than 80 range. And I will note that there's way more cases retrievals here, and so there are non-zero values in this range. Looking at over those 7 years, how many detections were happening where? Most of the detections of dust from long wave occur in sort of eastern New Mexico, West Texas, heading up into the Great Plains, some in California and Nevada. What's interesting about this, though, is it doesn't exactly line up with Daniel Tong's analysis. So he was using the surface monitors. You can see there's a lot in Arizona. We're not seeing much in Arizona. And we think this has to do with the dust in Arizona being convectively driven. When you have convective clouds, you get convective anvils. Those anvils block the satellite from being able to see the surface. And so we can't see the Arizona dust, whereas the Texas dust seems to be more regionally driven, and we are able to see it. On the other hand, you can see a lot of these epicenters happen to be where there's no monitors. And so the dust is seeing dust, the satellite's seeing dust in places where the monitors aren't. So in aggregate, the satellites we find are only detecting about 10% of the PM coarse or dust events measured at monitors. So they're missing quite a bit. But at the same time, when the satellites do see it, 90% of the time, those plumes that the satellites see do not touch a monitor. So it's clear that we need both at this point in situ monitors as well as satellite information to get a more complete picture. And one of the things Jennifer did is she used machine learning to actually cluster to detect dust plumes on their own. And this is this algorithm that tries to separate dust plumes so we can understand dust event frequency and size, sort of like a number size distribution of dust events. And just one tidbit from this, what she found is that about 9 plumes per year reach a size greater than the size of the state of Maryland through this grouping technique. So some of these plumes are enormous, these dust plumes. Finally, I just want to give a shout out for what we might be able to be bringing in with Tempo, or what we as a community might be able to start bringing in. This is again looking at New Mexico and Texas. There's dust in the true color here from this desert that looks slightly browner than the dust coming. This is White Sands, New Mexico, and the dust that comes off is visibly whiter, as you might expect. And you can see this is from that pink dust index from GOES. It sees the browner dust much better, but it hardly detects that white sands. And this shows that the ability for the long wave detection depends on the composition. And that white sands dust isn't really able to be detected from the long wave algorithm. However, this is just a preliminary product from the Tempo data. This is the UV absorbing aerosol index for the same time. And as you can see, here's white sands actually itself stands out. But you can see much more obviously the plume from the white sands also being detected along with the more brown plume. So to conclude, satellites offer the potential to augment our surface monitoring of dust events. Over 90% of satellite detected dust events occur away from our ground monitors just because they're so far apart where dust happens. There just aren't enough monitors there. But we need more work to improve satellite-based dust detection, and Tempo should be able to add a lot of information. Thanks.
All right, thank you very much. Next, we have Chelsea Langer from the New Mexico Department of Health.
Thank you. All right, so I always like to show off New Mexico when I can. So White Sands is in the bottom left when it is not blowing the sand around. So just some quick overview of New Mexico. It is the 5th largest state by area, so it doesn't compete with Alaska, but it's still pretty big. We're also the 36th least populous, so 45th in population density, so a lot of rural areas. Very varied climate and geography. We're also a majority minority state, so we have the highest proportion of Hispanics. It hovers around 50%. Second highest proportion of American Indian and Alaska Natives, with about 12% of the population identifying as Native American. And we have 19 Pueblos, 3 Apache tribes, and Navajo Nation as well in the state. So I work in the Department of Health. I'm the Bureau Chief for the Environmental Health Epidemiology Bureau. We are a centralized health department, so we cover and serve the entire state. And our bureau covers anything to do with the environment and health. So I've listed the programs here. These are all federally funded. Apple Tree is funded through ATSDR. It's the acronym that starts with an acronym. It's really based on Superfund sites and public health assessments. We have the asthma control program, obviously very interested in air quality. The biomonitoring program measures heavy metals in people's urine who live near active and abandoned mines. Childhood lead poisoning prevention program, all the lead talk earlier. Environmental health capacity is really focused on private well quality. And then environmental public health tracking, which I'll talk about more on the next slide, really covers the bulk of the climate work that's done in the state. And then we also have occupational health surveillance as well as wastewater surveillance. So for anyone who's not familiar with the tracking program, it's a CDC-funded network of 33 jurisdictions. Our main product is this public-facing portal where we have a variety of information about environmentally related health outcomes and environmental hazards. And then that's our homepage, and then the fire and smoke page, which always gets a lot of traffic when there are wildfires. So I'll just give some examples of the health outcomes that we generally track and are interested in, especially as they relate to air quality. So the next few slides, it'll have a map on the left. The darker red is bad, the lighter is better. And then it'll be trends over time. So this is for cardiovascular emergency department visits from 2010 to 2023. So you can see the Southeast region has the highest rate. That's also where the Permian Basin is, so New Mexico is also the second highest producing for oil and third for natural gas, which is mostly concentrated in the Southeast region. And then if we look at cardiovascular visits by sex, you can see males generally are the top line and have higher rates than females. Asthma is another big one that we monitor, especially in conjunction with our asthma control program. So again, highest rates in the Southeast region. And then the graph is looking at childhood asthma versus adult asthma. So childhood asthma has a much higher rate by quite a lot. And then there was the drop in 2020, and then we're creeping back up. But children are consistently higher for visiting the emergency department for asthma. So then if we look at that more carefully, the trend holds. The highest for childhood asthma ED visits is in the Southeast region, which is the top line. This is broken down by region. So the Southeast is again the highest. Now to get to the air quality side, as Jeff mentioned, air monitors are really sparse. New Mexico is really big. So we have 5 counties that have PM 2.5 regulatory monitors, basically hitting the main population centers. So Bernalillo County is the one in the middle that has Albuquerque. Doña Ana is down in the middle with Las Cruces, and then Lee in Hobbs is the one in the Southeast region, and then Santa Fe and Taos. We also have 5 counties that measure PM 2.5. You will notice they are not the same counties, but still very sparse. And then a quick shout out to Olivia Sablon, Jeff's student who came and spent an internship with us in the previous HAQAST cycle. So she was looking at PM 2.5 from smoke during the big wildfires in 2022. And the map on the left is looking at satellite data with the air monitors, and the one on the right brings in information from the low-cost sensors. So you can see the one on the right, you can really see where the Calf Canyon Hermit's Peak fire actually was, whereas if we just look at monitors and satellite, we don't really see it. So if I forget to state earlier, the point of that is we need low-cost sensors. Now looking at dust in 2025. So this year, there were, in the first part of the year, 169 dust storm warnings issued statewide from the National Weather Service. On average, we usually get about 4 of them a year. So it was extremely exceptional year. And this was really disruptive. Schools closed earlier altogether. We got sent home more than once. And then offices in the South got sent home even more often, mostly because it wasn't safe to travel because you can't see. So when I was getting ready for this talk, I asked various people in our bureau and like former colleagues, you know, what do you want to know about dust? Like, what do we want to know? That's the next slide, sorry. Questions we get are, you know, what is the impact on health from the Permian Basin with the oil and gas production, with the air quality in southeastern New Mexico? This is of particular interest to legislatures. So there's been House Bill 35 last session. It's been introduced a couple of times. It hasn't passed. I'm assuming we will see it again in January, where the legislatures are trying to get a children's health protection zone around oil and gas rigs. And then, you know, especially when there are wildfires or when there are these big dust storms, we get people who call in and say, you know, is it safe for my child to play outside? Can they go outside for recess? Can we have practice outside? And then, you know, the general, like, how do I protect myself? How do I protect my kid who has asthma? And then when asking colleagues about, what we want to know about it. Mostly it was summed up by like, what is actually in this dust that is blowing around? Like, does it include aerosolized byproducts from oil and gas? Is there PFAS that evaporates from the water? Holloman Lake is also in the southeast region near an Air Force base down by White Sands, where some of the highest levels of PFAS ever recorded in wildlife came from Holloman Lake. Does the air have heavy metals? What's the inorganic versus organic? With all the dust storms happening during the spring, there was a lot of question about like pollen and allergens in it. We also had a fellow working on valley fever. So, how much of that gets airborne? And then to the point earlier about the low-cost air monitors making a better picture of what's actually happening, what are the options for low-cost air monitors, and what monitoring is there for PM10 if we're not using or to supplement the regulatory monitors. And then this picture is the weather person or news person. This is not our state climatologist, but the state climatologist was wondering if there were high-resolution dust images of the most recent spring season, and particularly Roswell has been a hot spot for dust, and there are no monitors in that area. And that is all. I will leave it at that.
All right. Thank you very much for that. And now we'll be hearing from Jingqiu Mao from University of Alaska Fairbanks again.
Thank you. I'm really glad I'm able to talk after Jeff and after Chelsea. Actually, I'm going to try to answer some questions you guys raised in your talk. Okay, first of all, highlighted dust in Alaska. Okay, first of all, I'm going to show a picture. This summer, I was doing field camping, driving with my grad students. I just saw zero dust. I don't know if you guys can see that. In the far end, there are dust. That's just our place. And yeah, you can see cloud above the dust. I was wondering, how can we know this dust? There are no any monitoring whatsoever in this area. It's nowhere in Alaska boreal forest. We're doing a field camping for new product formation, but I was just bored and I was looking at our window and see dust. And there's no way we can quantify that. Just make me think, okay, is there any way we can really quantify dust? So okay, before I go there, I do want to give a little bit of background of why people start caring about highlighted dust. This was a picture from Copper River Valley, this dust clouds. And you can see there are lots of yellow dust just close. Partly due to glacier retreat, because when glacier retreating, global warming glacier retreat, you actually expose a lot of bare ground. And glacier itself also, once it's retreating, is grind the rock, make a lot of powder. It's called silt. We call silt. It's blackish. If you get a chance to go to Alaska, I'm going to show you how silt look like on glacier. It's amazing. Black, fine powder, rich in iron, very, very much nutrient for phytoplankton. This is something in North Pacific people have been wondering for a long time. North Pacific is deficit of iron. If you put iron there, you can get the next ice age because you can suck up all the CO2 from the air. That's what someone called John Martin said in the 1990s. But it is of great interest that when dust got deposited to ocean surface, you can see this kind of greenish color. That's the phytoplankton is blooming, because this phytoplankton on ocean surface, when you get iron, they can grow rapidly. Then you can suck the CO2 from air. Then you can become a geoengineering project. It's just so intriguing. That's why I think NASA, this PIS satellite has part of the reason they're paying attention to this area, North Pacific, Alaska area, is ready to pay attention to ocean color, aerosol, optical property, so on and so forth. So it's interesting, very. And yet, we really have not done much in terms of on ground-based measurements. So we don't know how to quantify that. So only thing I could use is from this local DEC's monitors. BAM, Jeff mentioned that PM10, PM2.5, you need both. So here I'm showing you the blue is PM10, Orange is PM 2.5. The difference is dust, is essentially dust. And you can, this is annual cycle for different sites, for different areas. You can see in many places, in April, it's hard to say, but it's in April and October, it's spring and fall, you see lots of dust. That's the dust season for Alaska. It's there. And for some areas, you don't see so often. The Eagle River, I think Helena told me that someone told me they were in Eagle River. Maybe I forgot. Anyway, Eagle River is also a dusty place. And so there's lots of dust in Alaska. But how do we quantify that? Okay, the first thing we start thinking is AirNet. There are about 8 sites in AirNet can give you some information about dust, because AirNet can retrieve these cosmos particles that we actually, this nice thing about, thanks to NASA, they have 9 to 10 sites in Alaska. And then for many sites, it has a long-term record of AirNet data. So we were able to look at the past 20 years. And I'm not the expert, I'm still learning about this, but we do see some evidence of dust in Alaska for many places, not just somewhere you have lots of glacier, also pretty far north, like in the North Slope. Here it's hard to say, but the main point is that for many places we see in the spring and the fall, we see evidence of dust events in many places. And this is one evidence in spring and fall. And another thing, just make us wonder what else we can use. There's no monitor, no PM10 monitors, $10,000 or $20,000 each, and you need manpower to maintain that. What else can we use? Actually, I'm starting to think about using this thing called automated surface observing system. It can measure visibility. Each airport, there's about 100, 200 visibility sensor in Alaska, which you can use for like 30, 50 years. We can use this visibility data to maybe quantify dust. Because in Alaska, again, as I mentioned earlier, that it's pretty simple. There are no anthropogenic emissions. We are either dust or wildfire smoke. So if you have low visibility events, either due to precipitation or due to air pollution. So this is something that, again, my student Zui Donghe has helped me to analyze data. We do find that once we see low visibility, we do see high dust events. For example, if you look at Anchorage and Juneau, some places, once visibility is low, we can see that PM10 is high, PM2.5 is low, that's dust events. So that's evidence there. Indeed, there's some information we can get. Okay, so this is another piece of information we could use. And here I want to introduce the first tool. We currently have a one-site called a SAND site. This is a new network established by the National Science Foundation. We're having this site in the middle of Boreal Forest. We have 4 instruments. This 4 instrument costs about $500,000, so we cannot set up too many sites like this. But one instrument on the bottom right is called XRF. It's to measure the X-ray from metals. We can use that to quantify metals in the particles. That's something we're hoping to use that to quantify the dust concentration from chemical perspective. And well, one more thing recently got me really interested is that another resource that I discovered recently in the last few months, FAA actually put lots of cameras in Alaska. I think many places, but this each place FAA camera has 4 cameras. Basically, you look at 4 angles. And there's a colleague from MIT Lincoln Lab. They actually have an algorithm to use 4 cameras to calculate visibility from the 4 images real time. So basically, every couple minutes, you get the visibility for each site. You can see that if you look at the left panel, there are about 400, 500 sites. You can get a visibility in real time. This is a very rich data set. That's just, I'm trying to convince them we can actually use machine learning to do a better job. Maybe we'll see something really still we're developing right now. But it's a way really to provide you some surface information from all the stuff we have there, infrastructure. This is also, I'm pretty sure it's pretty rich in lower 48. That's how we call you guys, lower 48. It's because we're in Alaska. But there are lots of cameras in continents and which can be used. So overall is that at the end, of course, HAQAST, we're trying to use satellites. We're trying, but it's hard to do satellite for Alaska because A, we have lots of clouds. B, we have snow on the ground. how do you use satellite? The retrieval, often when you retrieve AOD, when you have snow and ground, it's often not so easy to do. So we're trying to collaborate with Xi Chen and Juma at University of Iowa to look at this UV AI from TROPOMI and combine with aerosol layer height product, then hopefully we can identify some dust from satellite. But TROPOMI only give you, the overpass once a day, and we do not have ghosts. Ghost is kind of really, pretty weird view. It's not that trustworthy. So satellite is not that easy to use. I prefer to use ground-based measurements first before we can really move on to satellite. So this ground-based information, I think, is rich and a lot of potential to discover. We just need to build some confidence to put things together, to have a framework to understand, to use that data to quantify dust events. So eventually, we're hoping to have a framework, and with the wildfire dust and the other ground-based surface satellite together, we can do a better job on air quality forecast and nordcast for Alaska from now on. With that, thank you for your attention.
So the last speaker of this session is Patrick Reddy from University of Wisconsin-Madison.
Hi, everyone. So I'm going to talk about using Google Earth Engine as kind of a laboratory for assessing ozone, smoke, dust, and other pollutants. My interest in this platform actually comes from reading a tutorial by Jennifer and an article she wrote a couple years ago with her colleagues. And I see my role and also this platform as something that lies on a continuum between fundamental applied science and policy analysis. And Google Earth Engine is actually really well suited for this. I'm going to talk about 3 applications where I've used this. One is the HAQAST smoke console, which is for analysis of potential exceptional events by state, local, and federal agencies. And these events are associated with smoke or dust. The other is the Tempo Explorer, which provides comprehensive analysis of NO2, formaldehyde, the ratios between those, ozone, meteorology, and smoke. I'm doing this for the Utah Division of Air Quality as part of a Science for Solutions project. And the other topic is about various apps applied to Africa. So this is a screenshot from the HAQAST smoke console for July 22nd of last year. And that was the day when smoke was dropping southward across the Canadian border, and black carbon flux vectors are the little arrows. The red shows high flux of black carbon, and that's from the MERA-2 reanalysis. I have a smoke mask, which indicates high probability for smoke over your area based on 90th and 95th percentile values for TROPOMI CO and or surface black carbon from MERA-2. And you can see that this blue mask surrounds a whole cluster of ozone exceedances in orange in the Rocky Mountain states and the upper Midwest. So if you have an exceedance of ozone or PM2.5 under that blue mask, and you look at a bunch of the other 21 layers that are in this, you can create a good case for excluding an event as an exceptional event. The program doesn't handle domestic dust very well, but the MERA-2 surface dust PM2.5 product does show dust transported from the Sahara quite well. And this is an issue for states along the Gulf Coast and Texas. And I've got dust flux vectors. The red is really high levels, and also contours of the surface dust concentrations, and exceedances of the 24-hour PM2.5 standard show up as the red and orange symbols. And MERA-2 overestimates the dust quite a lot, but it gets the contours, the arrival times, and the shape of the dust plume really well. So it's a good tool for identifying exceptional events. So for the, and you can access this, the user's guide, the raw JavaScript code, or a web app version of it at these sites. For the Utah project, I've been wanting to use tempo data, and I was starting to learn how to access it with RSig when I discovered that the tempo data, level 3 QA data has been added as data sets for, or in Google Earth Engine itself. So this was exciting for me, and I created a Tempo Explorer program, which has a number of layers and variables in it, including level 3 tempo NO2 and formaldehyde for hours 13 to 23, vector mean real-time mesoscale analysis surface winds, and a low wind speed mask, daily max and hourly ozone, and then sliders for hour of the day and also the cloud fraction for the retrieval. There are also high and low of ozone event filters, weekend, weekday filters, smoke indicators. I'm using the same smoke indicator from the other product here. And then I've also included an ozone production regime analysis routine based on the ratios between formaldehyde and NO2. And I'm following the method of Xiaoming Jin and Arlene Fiore and others in this, and I generate a complete statistical report on the success of the bootstrap method. This is a screenshot of the program. When you're doing this test, you can select as many monitors as you wish. If you select too few in the wrong place, you're not going to get a good result because there's not enough hours above the threshold value for the analysis. But anyway, the beauty of this part of the program is that you can not only see hourly FNR values in your region of interest, but then you can calibrate the region sensitivity in terms of whether it's VOC sensitive, transitional, or NOx sensitive. A VOC sensitive region responds poorly to NOx reductions, ozone goes up. The transitional regime responds well to both VOC reductions and NOx reductions, and then NOx sensitive, you generally want to reduce NOx emissions. So with just one season of data for Denver, the results are good enough that you can get a snapshot of where you stand in terms of those regimes at each monitor. And also in this case, I selected the downtown Denver monitor in the right panel. And I had it map the regimes for all the days when that monitor was above the standard. And the VOC sensitive region is in gray. I've smoothed the data that goes into this quite a bit, so it's not neighborhood scale, but it does pick up high traffic areas, DIA, and most of the area is actually transitional. I'm testing a tropometer version of this as well. On the right panel, there's more reports you can look at, including the curve that's fit through the data to come up with the regimes, and then a bar chart that shows how all the exceedances in your collection of monitors are distributed across the regime. So the Denver metro area is predominantly transitional and NOx sensitive, and that's also true for Salt Lake City and Las Vegas from what I've seen so far. There's other things you can do with the Tempo Explorer. In this case, I've selected in the little red circle an Evergreen Colorado monitor, which is a foothills monitor It has high ozone when there's thermally driven upslope flows from Denver. This is a mean for all the high ozone days at Evergreen, and it shows what the regional patterns look like on those days. So there's thermally driven upslope flow from Denver, a upslope, downslope convergence zone. Monitors that are in that convergence zone are more likely to have high ozone, and those that are east as well. But if you're west, not so much. On the right panel, there's plots of the exceedance days, and then the smoke flag index. And you can see that the high smoke days tend to have higher ozone. One of these days is the one that I showed with the HAQAST smoke console earlier. There's also plots of hourly formaldehyde and NO2 at that site on both clean days and high ozone days. And you can see the effect of late day arrival of precursors at that site on high ozone days. And I just want to mention this lower right chart is a plot of high ozone days with smoke. They're the hourly ozone profiles, and high ozone days without smoke. This is the kind of information that can be useful in exceptional event reports and also in ozone state implementation planning to exclude days from the design value targets. Exclude days affected by smoke. So I also have been working on platforms to look at air quality in Africa, and most of the poor air quality events in Africa are associated with Saharan dust or biomass burning. And in these two maps, I've plotted fire detections in the bottom, NDVI. Most of the fires occur in a certain NDVI or greenness index range, and high NO2 tends to be clustered over those fires. And here's an example of that. I've circled Coma A National Park in Cote d'Ivoire, and I've plotted NO2 in December on this map. Most of the national park is a World Heritage Site, and it's a savanna primarily, and they burn the grass in December. I was curious to see how that NO2 correlated with precipitation and greenness indexes. So I drew a polygon in the app around the park, and the NO2 anomaly aligns perfectly with the boundaries of the park. And I found that NO2 over the park is positively correlated with November rain and inversely correlated with December rain, and that makes sense. The grass biomass increases with a wet November. If it dries out enough, then the emissions in December are higher. NO2 is also inversely correlated with NDVI over like a 2 or 3 month period. It would be possible to combine all those in a model, use that as a baseline to track interventions and whether or not they're successful, and to look at long-term patterns in weather and how they affect burning emissions. So that's all I have. I guess I will mention this last image here is an 8-day composite of tempo, formaldehyde, and NO2, and the surface vector winds at 2 fires this last summer. The fires were burning steadily for 8 days with a steady wind direction at the surface and loft. And it's possible with this tool that you can draw a transect across the fire or along the length of the plume and see hourly changes in formaldehyde and NO2 by distance. And this is only with the cloud fraction setting set to 50%. If you drop it to 20%, the plumes disappear. But for the purposes of an exceptional event report, it can be really useful to look at the smoke itself, and that's why I have that filter designed so you can set it to 50%. Thank you.
All right, thank you very much. And we'll bring our speakers up to the front for Q&A. So I think something that was pretty common to all of these presentations was kind of making sort of the maximum use of everything you have. So bringing in satellite data, low-cost sensors, visibility from airport cameras, and bring all that information together. And I think Patrick kind of summarized that by showing how a tool like Google Earth Engine can bring all these data sets together. So to start off the discussion, maybe we'll go back through the presenters and talk a little bit about sort of what's your approach to integrating these diverse sources of data? How do you kind of think about tackling that challenge? What are some of the tools in your toolbox there, and what are some of the things you might want to see developed in the future to make that problem of kind of bringing these diverse data sets together a little bit more straightforward for you, I guess. We'll start with Jeff.
Oh,
You have a-
going to me.
Yeah, we can.
Sure. So I guess a lot of what you're talking about has both in situ monitors at specific locations, tells you everything you want to know precisely, but only that one spot, along with satellite data, though. Yeah, you were talking about visibility. I actually have a question for you about how you tell smoke. You talked to us about smoke in the last session, and I'm like, how are you going to tell smoke from dust? Anyway, yeah, I mean, traditionally, I think things like geo-weighted regression could have let you get at that, and now the big black box of machine learning, hopefully you can understand a bit what's happening under the hood there, could help get at blending this to try to make spatial temporal maps. Yeah. I don't know who wants to go next.
Chelsea, next maybe.
Sure. So I think we look at it two different ways. And for the longitudinal, looking at health trends over time, then incorporating satellite data monitors, hopefully low-cost monitors, is really exciting and helpful. For decision-making in the moment, I think we're going to focus on more low-cost sensors. So I wasn't quite confident enough to put it in writing, but we are starting an initiative to buy low-cost monitors and put them based in schools with targeting the rural areas that don't have current monitors. There was a really great article from Montana where the state health department partnered with the university and got science teachers involved. And I was like, science teachers are the perfect people for this. So we're in the very early planning phase of it. But I'm really excited, and I think it'll be really useful, especially because we do get a lot of calls in the moment of, what is the air quality in my spot, and like, can my kids go outside? And it's really hard to say when we don't have a monitor.
Yeah. Yeah, go ahead.
So
I think it's on. Beyond.
So I worked at the Colorado Department of Public Health and Environment Air Pollution Control Division for a couple decades. And I was a forecaster, and I also worked on ozone state implementation plans, exceptional event reports, and they allowed me to do some research too. And I got really interested in satellites for our work maybe 10 years ago. I always look at what this data can do from the perspective of a former state regulator and their clients. And their clients are often regulatory bodies, commissioners, legislators, sometimes governors. And so I like the idea of pulling together products that serve the staff in those kinds of agencies, the scientists, the people that understand the data really well, and also their clients their bosses, attorneys, scientists at the EPA that are going to review their work. And I think that's really exciting.
Okay.
Thank you. For my research or in general, working with different stakeholders, our approach, first of all, we know purple air cannot see very small particles, less than 100 nanometers. Purple air cannot see that. Once higher than 700 nanometer, purple air can barely see, that's just not sensitive. So it's important to understand the low cost sensor. You should keep in mind that is low cost sensor. That's something you cannot treat as a research grade instrument. And then we know strengths and weakness, and then make sure we know the ground truth by combining different tools. That's kind of a thing we really want to make sure, because once you get purple air, you got reading of 200, but maybe it's only 50 microgram per cubic meter. That's something we need to do a little bit of QA, QC. I think that's really first step right now. We want to make sure when we compare different sources, we have a ground truth. That's something I would think that DEC, like beta attenuation monitor, or FRM, FEM. FRM only you can get a filter once a day. FEM is better. You get hourly data. That's maybe better, and then you can use that to start from there. And then when you get a ground truth, you can use that to better combine other things. That'll be my approach.
Okay.
Oh,
Yeah,
we
go
just have a question online that's extremely relevant. I think you kind of answered it, but just if anyone else has something to say on it. Tanvir Khan asked about low-cost sensors being not reliable for coarse particles for PM10 and even PM2.5 ratings being uncertain. And how do you approach using the low-cost sensors for monitoring for coarse dust events? So if anyone else, I feel like you kind of answered that just now, but if anyone else wants to.
Yeah, I'm actually really glad that Jingqiu mentioned the quantifying because it's about getting some for course. But for the purple air, I mean, they don't. It's actually I really wish they didn't publish a PM10 value. It's dangerous because if you take all the purple air measurements in the US and you plot PM10 versus PM2.5, they almost fall on a line. There's a little bit of deviation from it, but it's basically just like they take their PM2.5, multiply it by some factor, and they get their PM10. It doesn't actually make it in the inlet if it's above 2 microns or something. So yeah, I think by and large, the lowest cost doesn't measure coarse at all. I had hope for the quantifying, which uses the alpha sense whatever in it, but maybe that's not that great either.
It's probably it's good. It has a optical particle counter in there. It's a different principle than purple air, but we just need to have a closer look at the data, making sure we understand that. Because right now, when we look at Alaska, it's maybe a different dust than California dust. From the documentation I read from Quantum they have pretty good agreement between PM10 from EPA and the quantum for the California dust or somewhere else. But for Alaska, it's not quite the case yet. We're trying to understand why.
Okay. Questions in the room? Yep.
Hi, I'm Ping Jing from Loyola University Chicago. I worked with the CPS, Chicago Public School Teachers, this past summer using portable air sensors called AirBeam 3. Because teachers, they like that because it gives you this map in real time. And my question is, how reliable are these portable air sensors? If you have any knowledge of it.
It's also another variation of that power.
Yeah. Yeah, I don't know it. Yeah, a lot of them use the plan tower, which is the same thing that Purple Air has. So I love Purple Airs. I don't want to diss it. It's great for PM 2.5. It needs some corrections, but if it's similar to that, I think for educational purposes and for filling in gaps, like it's incredible. It's great for wildfire smoke. You just need to correct it the right way. So I think it's awesome to do it. I just would be skeptical if you're looking at coarse particles for sure. But for PM 2.5 and working with teachers, that's awesome.
Maybe, I don't know if anyone's close. Okay.
Well, yeah, and I'll echo it's tough with low cost sensors versus FEMs and seeing both those products. I'll echo that. But I had a question, Chelsea, how much, because you're with the Health Department of Mexico, if I'm not, and how much collaboration do you do with, say, the environmental side in New Mexico on like mitigation plans or anything with high wind dust events?
Yeah, we collaborate really closely with, well, our bureau has all of the counterparts in the environment department. So for this, we collaborate very closely with the Air Quality Bureau, and they're the ones who well, between them and the U.S. Forest Service, if there is a wildfire, usually that would be the Forest Service goes out and deploys monitors. They're not always the best at sharing the data, but there are monitors out there. And then last week, on Friday, there was an explosion at a refinery. And so NMED went down with monitors to work on it. So yes, we do work closely with them. Yeah, and they're great. I'm going to try to get them here next time.
Any other questions in the room or online? So, oh, yeah, go ahead. No, go ahead. Oh.
This is just a follow-up comment from someone online from Tanvir Khan, who had said, we have 2 co-location studies going on, one in Florida and one in Georgia, where we have sensors from several vendors, including low cost and mid-range, and are being evaluated against FEM and FRM monitors. So anyone interested in learning more can reach out, and I'm happy to help connect folks on that. So it's happening. That's all.
All right. Oh, question.
Hello, Adam Saucer, MIT. So this question, I guess, is to any panelist who dares to answer this question. It could be kind of an off the rails question, but so I asked this question from the perspective of somebody who thinks about water quality. And the reason why I'm asking this question is so in our models, we have to make certain assumptions about dry and wet deposition rates of certain contaminants. So I look at just that example of the map up there, which if I can appreciate it correctly, it shows concentrations of a particular set of pollutants and contaminants. I would imagine that you could glean from that a corresponding pattern of deposition rates. And I guess my question to you is how difficult, how easy is that? And how could one get in contact with you to get that sort of data, or even think about translating that data into a model that tracks water quality? And again, these deposition rates are really important to the subsequent outcomes. So thanks.
You or me? Yeah. So Jingqiu and I both run chemical transport models, or groups do. I don't do it anymore. So that's part that physics is in there for all the species we track. But certain species, I guess my answer is it depends, like how well we know it depends on the species. For aerosol species, it greatly depends on the size and the land cover type. And so getting those right is critical for getting it. For gas phase species, it depends on how sticky it is. Things like ammonia are particularly tricky because it depends on how much ammonia is in the ground, or like what the acidity of the ground is, and if the ground has if it's fertilizer, it's emitting ammonia. If it's a forest, it's taking up ammonia. But yes, in general, the chemical transport modelers are doing that calculation. So you could, in theory, do it with measured data as well, using the same mathematical functions. Yeah.
Maybe I could. I know for Alaska that when we have wildfire, people have quantified the organic matter from wildfire deposit to the water. that's found that the water organic in the water is enriched due to wildfire. So there are some observational evidence for that. But then if you want to quantify that, it's hard to validate your model unless you have very well-designed experiment to address that. It's kind of a multi-million dollar question, I think.
There is the National Deposition Monitoring Network, which for some species, particularly ions and whatnot, gets, I can't remember if organics are in that, but
You have
yeah.
buckets and
Yeah.
you have black bucket, you can measure those things.
Yeah. Sulfate, nitrate, ammonium,
Yep.
those things.
Other questions in the room or online?
When do we have to entertain you till?
I think we have 10
10 more minutes.
So to I guess another kind of broad discussion topic for the group, the value of quantitative versus more qualitative indicators. So for example, you're looking at the formaldehyde NO2 ratio. That's, a little bit more, it's a quantity, of course, but it's a little bit more, qualitative, but it provides very important information about what regime you might be in and what the source of the ozone is. And then similarly for dust, we have, these dust detection products, which are not, they're quantitative in a sense, but qualitative in a different sense. So I guess the general topic for discussion, whoever wants to opine on it, is relative value of things that are more qualitative versus more quantitative in what you do from a day-to-day basis, and how you might think about what tools or products might the HAQAST focus on in either of those areas to improve in the future.
So with the state exceptional event or local agency exceptional event reports, what's required there is sort of a weight of evidence that something happened, and you don't need absolute proof. And so a semi-quantitative index can be useful and really important in that context. Also in ozone state implementation plans, if you have 3 years with a bunch of smoke exceedance days, the EPA will let you make an argument that some of those should be excluded from the design value targets. And that process also can be swayed by less than purely quantitative evidence. So if you've got something like that hourly ozone chart I showed, it doesn't prove that smoke caused the ozone, but it, combined with other things, it's good evidence for that. But in other contexts, a lot of regulatory agency work does require harder science, if I can put it that way.
Yeah, I mean, I think for dust detection, I mean, even just a qualitative binary indicator, like the long wave would be useful if it's reliable. I think for a lot of these things where we just don't have monitors, knowing that we're having some bad event is better than nothing.
I'm gonna want to add one thing, depending on what the purpose is, I guess. If you want to just look at as general public want to use that information for hiking, for fishing, then that's relative change would be actually very useful. That's all you need. You do not need absolute amount of PM2.5 value. But for model evaluation, that's a different purpose. So for those purpose area, when we look at relative change, that's actually sometimes good enough, tell you whether it's smoke or not. Binary answer, you need that, that's the real purpose. So really depends on the purpose, then we can make a right decision.
I had a thought, like just thinking when Jingqiu was talking, the NOAA hazard mapping system, which is a satellite product where trained analysts look at visual images from satellites and draw polygons around where smoke is, has been used both for so much communication as well as science. And so I guess it's 3 levels of smoke, but it's been amazing. So yeah, I think there's a lot of value.
Yeah, and the EPA fire and smoke map overlaying
Yep.
that, the polygons, the low cost, it's not necessarily quantitative for any given location, but it gives you a good
Yeah.
sense of awareness. I think that's the same general idea. Oh, yeah.
Hello. I have a question for Chelsea. As someone who's been researching dust storms a lot, obviously, and seeing a lot of dust storms in New Mexico, I was curious as to what the general like public outlook is on dust storms, and if it's something that's just kind of like an annoyance where it's like, oh, it's just our reality. Dust storms happen, or is it something where the public is getting pretty outraged about dust storms?
Good question. So I grew up in southern New Mexico, and dust storms were definitely an annoyance. Especially when like the dirt gets in your teeth and it just like stings your eyes and like makes it really unpleasant. Now there's getting to be more annoyance around the state, bordering on, I think, anger, upset. Like this is actually really a big issue when people are getting sent home because you can't see on the freeway. So like they'll close I-25, and like we had people come up from Albuquerque and they couldn't go back to, they couldn't get home on the freeway, so they had to go on this whole long circuitous route because the interstate was closed because you can't see. And then schools closing because kids can't get there safely and get home. So it definitely became much more of a statewide impact this year than it has ever been before. Historically, it's always been a southern New Mexico problem. Yeah.
Thank you.
And thank you. I love all your pictures. I can't wait to see your poster.
Hello, this question is for Chelsea. So, do you guys work with TCEQ, like in southern New Mexico and like El Paso, Texas? Like this is a big problem. So, do you all collaborate with like Texas Commission on Environmental Quality, and then on the other side of the border with the state of Chihuahua, because that's like a tri-state, I mean, binational tri-city area. So, any input on that?
Yeah, good question. Our main person with the environment department who focuses on dust is based in Las Cruces, as well as the state climatologist. So they work closely with people at UTEP, and I believe people also across the border in Texas. Across the border in Mexico, sorry.
Ciudad Juarez.
Yeah, Juarez.
Okay, I have a question. Earlier this year, I was at a drought and health workshop, and so a lot of the similar topics with dust came up as sort of in the context of sort of thinking about longer term drought trends. And I'm wondering how, if you've seen any trends with drought and dust and health, or if you would expect to. It's interesting to hear you guys talk about like the different sources of dust and how they're composed differently. So I'm kind of curious how that ties in with the health effects.
Saying how it's just gonna solve the New Mexico problem. No, it's not.
Yeah, so with the drought, it's definitely become more of a statewide issue. And then really what helps it go down is once the monsoons start, which if there's a bad monsoon season when the monsoon doesn't come, then it's just constant. And then there's drier, so more dirt to blow around. We need the state climatologist here. I think he made a poster on this.
Yeah, I know there's been some work on trends and projected trends based on climate models, which has dust projected to be an increasing problem similar to wildfires because of aridity.
Did the panelists have questions for each other that they want to? Oh,
So I have a question about Saharan dust. I used to think that PM10 settled out rapidly, but when the Saharan dust hits the US, PM10 is still high. PM2.5 is high. I know a lot of that dust fertilized the Atlantic. Just curious about how quickly and differently do the different size fractions deposit?
I wish I remember the paper's authors' names, but there's work out fairly recently on how the Saharan dust, the heating, because it's a somewhat absorbing aerosol. When the dust gets heated, that layer gets warm and it helps the dust stay off. So it's actually a problem for deposition. Like the models don't necessarily get the deposition right because we're not getting the self-heating and rising right. And so that's because it was this related to this question of why is the PM10, why is the course mode making it across the Atlantic? It shouldn't if you just don't consider that. And so it's fascinating. Anyone else? Anyone in the room know what I'm talking about? Yeah, red makes
Fox group?
yeah, that would make sense. Yeah.
All right. Yeah, we're at time. Oh, okay. So yeah, we're just about at time. Thank our speakers again. And announcement.